Welcome back, class. Today's lesson is about torque and rotational statics. That means things that are not necessarily rotating at the moment, but they have rotational forces on them. So what we're talking about really here is, so far when we've dealt in two dimensions, which is mostly what we've done, we've talked about two different kinds of motion, right? We've talked about X and we talked about Y. Okay, X is to the right is positive. Y upward is positive usually. So, well, if you have a rigid body stuck in two dimensions in the plane, there's one other way it can move, and that's rotation. And in rotation, we take as a convention that counterclockwise is positive, which seems a little weird, but if you think about the XY plane, you may remember that this is the first coordinate, the first quartile, the second, the third, and the fourth. So, as you go through the first, second, third, and fourth, you're actually rotating counterclockwise, and that has to do with where it comes from. So, what makes things move in the X direction? Well, that would be the forces in the X direction. And in the Y direction, things move because forces in the Y direction. Interestingly, what makes things move rotationally is what we call torque. And it's a Greek tau. Torque. So that's what we're going to study today. Now, turns out that if you have, say, some particular object, and let's just say that it has a pivot point right here, and you put a force right here on that object, well, it turns out that if we take L equal to the perpendicular distance from that force to that pivot point, okay, the perpendicular distance there is L, then we say the torque is equal to F times L. And that's our basic torque equation there. But this piece about perpendicular is very important later on. And I'll give you some examples. There we go. In this example, we have a woman standing on the end of a diving board. It says, a woman whose weight is 530 newtons. Okay, so let me start drawing this out. All right, basically what we've got is we've got this diving board. And there's a fulcrum right here. There's an upward force, and then there's a bolt pushing downward on it right here. All right, and we're told that her weight is 530 newtons. Okay, so she is a downward force of 530 newtons. Okay. Poised at the right end of the diving board with a length of 3.9 meters. 3.9 meters from end to end. Okay. The board has negligible weight and is bolted down at the left end, which is being supported 1.4 meters away by a fulcrum. Okay. 1.4 meters from here to here. All right. Find forces F1 and F2 of the bolt and the fulcrum respectively. So this is F1 and this is F2. And that's all we're given. But now we have not only our original Fx and Fy equations for equilibrium, but we have a torque equation too. So let's take a look at what we have here. for instance, the sum of the forces in the y direction are going to equal negative F1 plus F2 minus 530 equals 0. Okay. Some of the forces in the x direction, there are no forces in the x direction, so I'm not even going to go there. Okay, now the next thing is the sum of the torques. Now I'm thinking to myself, why don't I just do this one? I've got F2 here and I've got a lever arm, nice and perpendicular. I've got the 530, I've got another lever arm. Let's leave F1 right out of the equation. That way we're going to have one variable and we should be able to find F2 just that easily. Okay, so remember, counterclockwise is positive. So that means that we have 1.4 times F2 equals, or I'll just say minus 3.9 times 530 equals 0. That looks like a pretty easy thing to solve if we want to solve for F2, right? Let's see. Can you see that F2 should equal 3.9 times 530 divided by 1.4? And if we calculate that out, we get 1,480 newtons. So, we've already solved the first part. Now all we need is F1. But we have this equation right here we can bring down. It says that negative F1 plus F2, which we know is 1480, minus 530 equals 0. Okay? So now where are we? If we want to solve for F1, well, let's see, let's put these two together. Negative F, by the way, this is F1. Negative F1, 1480 minus 530, that's 946 plus 946 equals 0. Therefore, F1 equals 946 newtons. Piece of cake. So we have this new tool. The sum of the torques around whatever axis we choose has to equal 0, and we can use that to create to solve problems where it's not enough just to know the sum of the forces. We can also take into account the fact that the object is not rotating. Okay, so I'm going to give you a problem to try. Let me just pause and I'll write it out. Okay, so welcome back. Your next lab you're going to be building mobiles. And so this is about a mobile. You've got a rod, which is a part of a moving sculpture. A mobile consists of a rod of negligible mass supported by a cable with two masses hanging from it as shown below. Find the masses. Okay, so we have a tension on the cable going up at 10 newtons. We have M1G downward here, M2G going downward here. We're told the total length is 4 meters, and the distance from the left side to the tension cable is 1 meter. So why don't you go ahead and try to solve that problem? And you can pause this for now while you're solving it. Okay, let's go ahead and solve it. Once again, all of our forces are in the y direction. None of them are in the x direction. And we can say the sum of the forces in the y direction are going to equal, let's see, we've got negative M1G plus 10 minus M2G equals 0. Okay, well, let's leave that alone for now, and we'll come back to it later on. What we want to do now, let's look at the torques. I think that's what's really going to help us out in this problem. So, I'm thinking I'm just going to measure from the left side. It doesn't really matter that much, but I've got the distances all set up, so I'm going to go ahead and do that. So let's see. We're going to do, we can do 10 newtons times 1 meter. Okay, that's positive because it's counterclockwise. Minus M2G times 4 meters has to equal 0. Alright, this should be enough to solve for M2G, right? Let's see. 4 M2G equals 10. M2G equals 10 divided by 4. Let's see, that would be 2.5 newtons. Now, we know what M2G is. We can find M2 from that. What about M1? Well, don't forget we have this other equation right here. We can bring this one down, and we can say negative M1G minus, now M2G is just 2.5. No, I'm sorry, over here, plus 10 minus M2G minus 2.5 equals 0. So negative M1G must equal, well, we can say negative M1G plus 7.5 equals 0. So M1G equals 7.5 newtons. Okay, this one here, this implies that M2 equals, well, let's see, don't forget, weight is mass. This is mg, so we divide by 10 to get m. 0.25 kilograms. And here we can see that m1 is going to be 0.75 kilograms. And that's all there is to it. I'm going to move on and do another example from the book. Okay, so we're looking at example 4 on page 250. It reads, in figure 9.7a, an 8-meter ladder of weight WL of 355 newtons leans against a smooth vertical wall. The term smooth means that the wall can exert only normal force directed perpendicular to the wall and cannot exert a frictional force parallel to it. A firefighter whose weight is WF equals 875 newtons stands 6.3 meters up from the bottom of the ladder. So you can see I've drawn this in here. There's our 8-meter ladder. There's the weight of the ladder, 355 newtons. There's the firefighter, 875 newtons. This P here, that's the force of the wall against the ladder, perpendicular to the wall. Now on the floor, we have, from the ground, we have an X and a Y component of the ground force. The firefighter's weight, okay, assume the ladder's weight acts on the ladder's center and neglect the hose's weight. Find the forces that the wall and the ground exert on the ladder. Okay, so there's P is the force from the wall, and ground has got an X component and a Y component. So what makes sense to do is we see this is an equilibrium situation. So we have the sum of the forces in the X direction equal to 0, the sum of the forces in the Y direction equal to 0, and we have the torques equal to 0. So let's go ahead and solve this problem. Let's see, let me just grab a pencil. Oops. This thing's acting up a little bit. Alright, pencil. Okay, so we have the sum of the forces in the X direction. Well, let's see, we've got G sub X. Alright, and then we've got minus P, and that has to equal 0. So that will tell us that G sub X equals P. Now let's look at the sum of the forces in the y direction. Okay, we've got G sub y minus 355 minus 875 equals 0. Okay, so let's see. If we add these two together, we're going to get G sub y minus 1230 equals 0. G sub y equals 1230. Alright, so that's one of the things we were asked to find. So we already have the y component of the force exerted by the ground. Okay, so now the next thing we have to do is the sum of the torques. So let's see, the sum of the torques. And what we'll do is we'll take the torques around this point here where the ladder touches the ground. That way Gx and Gy will exhibit no torque because they'll have no lever arm. So we'll only have a torque from WL, the weight of the ladder, WF, the weight of the fireman, and P, the force from the wall. So let's see. We've got, from WL, we've got 355, okay, and this is clockwise, so negative 355. And then we have the lever arm. This is the tricky part, because you see the lever arm is actually not this distance 4 meters. It's the perpendicular distance. If you were to take that force vector, bring it down, and look at the distance between there, it's basically this distance right here. The perpendicular distance from perpendicular to the force to the point. So that's going to be 4 cosine 50 because it's the adjacent. So that's times 4 cosine 50. Okay, so that's the part that's from the ladder. Then we have another negative torque here from the fireman. So that's plus negative 875 times 6.3. And once again, it's cosine 50. Plus the torque from P, the force from the wall. So that's P times 8. Now here's where it gets tricky, because if you look, if you would extend P across, the distance we're looking for is the height of P, the distance, the perpendicular to P distance from this point here. And so you can see we've got this right triangle, we've got 8 and we've got 50 degrees. We're looking for the opposite over here. This is what we're really looking for, this height here. So that's going to be sine of 50. And of course that all equals 0. Alright, so if we take all these numbers and we crunch them in our calculator, we'll end up with the torque equals negative 4456 plus P times 6.128 equals 0, which means that 6.128 P equals 4456. We can divide both sides by 6.128. Those cancel, and we get that P equals 727 newtons. Now notice here, G sub x equals P. So that's also equal to G sub x. So now we've solved the whole problem. We've got P, we've got G sub x, and we've got G sub y. So that's all there is to it. Alright, now let me get a fresh page so that I can give you a problem to try. Let me just pause it while I put... Okay, so here's your problem to solve. You've got a hydraulic jack here. The piston is pushing up with some force. It's trying to lift a weight that is pushing back down at it with 6,000 newtons. And you can see that the arm of this jack is at 40 degrees. The piston is applying its force 0.2 meters down the arm, and the weight is pushing down on the force 0.5 meters along the arm. So your job is to find F. Okay, give it a try, and then I'll see if I get the same answer. Okay, here goes. So this problem, if you look at it, if we did just the torques from this pivot point, we're going to have F times some lever arm plus 6,000, or negative F times some lever arm plus, F times some lever arm minus 6,000 times some other lever arm equals 0. So that's all we should need in order to solve this problem. So let's give it a try. We're going to do the sum of the torques is equal to, we've got F times its lever arm. That's 0.2. Now the question is, see, the lever arm is the perpendicular distance from the force. It's this distance here. So that's going to be cosine 40. And that's going to be minus 6,000, because that's going clockwise, so it's negative, times 0.5 cosine 40 equals 0. So if we do a couple of calculations here, we see that this is 0.153 F minus 2298 equals 0. So 0.153 F equals 2298. Divide both sides by 0.153. 0.153. Those cancel, and we end up with F equal to 15,020 newtons. So once again, what we did was we just did the sum of the torques around this pivot point here. That gave us F times 0.2 times the cosine of 40 to get this perpendicular distance to F, minus, because clockwise, 6,000 times 0.5 cosine 40 equals 0. So that's basically the whole deal. Let's see, why don't we go back to the beginning and just see what our basic concepts are here. So our basic concepts are that we have X, we have Y forces, and then we have rotation, which is torque. And torque is equal to the force times the lever arm perpendicular to the force vector. So for various different kinds of angles, we have to choose different distances to figure out the lever arm. Okay, because it's always going to be perpendicular to the force, the perpendicular distance from the force to the pivot point. So that's basically all I've got for you, and we'll have some problems for you to do in class. I'll see you soon. Bye.